that's tuning into this video. This is Team 8's ideas for the structural dynamics project. Um, in this case, as our project has assigned, a typical structural dynamics project includes designing, prototyping, a lot of risk and mitigation analysis, that includes FEA, as well as a vibrations test. The main point of the project is to just design and prototype a rocket and perform analysis and testing, then to compare the results. In a lot of cases, when we first start designing, the main function of a structural system is to transmit the loads from the forces generated during the time of flight and provide pretty much a low aerodynamic drag for flight through the atmosphere, as well as just a very smooth launch in terms of if anything's going to vibrate off or not. So in this case, when we first started off our project, we decided to do a individual conceptual design. The whole main point of it is to just at least give an idea of what everyone thinks that would be the best solution to the provided problem. And in our final design that was made in CATIA, we decided to do a hybrid idea between the Falcon 9 and Atlas V, taking upon the main head of the body as well as the length of it. And in terms of the fins, we took some inspiration from the Vulcan ULA rocket variant, having it act as if they're boosters in this case. In terms of just general prototyping, the best printer on campus to at least provide the project guidelines, which is at least max 2 feet. We wanted to at least have a type of rocket that wouldn't be pushing that limit, but also be the case where the bigger it is, the more stresses it can actually just spread out through the entire thing itself. So we decided to print with the Modix Big 60 3D printer, which printed our parts in 3 different ones instead of our typical 6. If we use the MakerBots, our main material was PLA, and in this case, this was the assigned material. If we were to continue this project, we would switch to a PLA Plus, just because it's a lot easier to handle, as well as it tends to at least take a lot more stresses than normal PLA, and as well as heat as well. In terms of infill, we decided to at least keep it pretty open to the ones printing this, just because all 3 of us don't necessarily have a very good technical aspect in terms of just 3D printing, so we left it up to the people in the RPL lab.
So with our rocket that we designed, we wanted to mimic the vibrations that it would experience during the testing. So we put our rocket into ANSYS and we constrained it at the bottom of the base to represent it being on the shaker table. And we looked at the first 10 modes that it would experience over a sweep of frequencies. The first natural frequency was at 88.6 hertz. This was seen by a bending motion from the tip of the rocket in one direction as the bottom stayed stationary. And the second mode was the same shape except in a different direction, and it also occurred at 88.6 hertz. Mode 3 was the first non-bending mode, and as the video shows, it is represented by a twisting motion. This occurred at 405.3 hertz. Mode 4 was the second pair of bending shapes. This happened at 436.4 hertz, and the bottom stays stationary, but the motion that it goes into is represented by a half sine wave in one direction. The fifth mode shape is the same as the fourth, except the half sine wave occurs in a different direction, and it still happens at 436.4 hertz. Mode 6 was a non-bending shape. It was represented by an up and down motion of the rocket, and this happened at 878.6 hertz. Mode 7 was another twisting shape. It happened at 1037 hertz, and in this shape, the whole rocket seemed to twist, except in the middle, there was a node where there was no motion. Mode 8 is the third and final pair of bending shapes. This happened at 1047.4 hertz, and this was represented by a full sine wave with 3 nodes in it. So the bottom, middle, and the top were stationary. Mode 9 is the same shape, the full sine wave, but in a different direction, and it also occurred at 1047.4 hertz. Mode 10 was the final mode that we looked at, and this happened at 1376 hertz, and this was represented by twisting of the fins just themselves.
So to go into a little bit of the actual vibration testing and validation, our goal was to find experimental values for the first 3 bending frequencies, and then to compare those values to the theoretical values we got in ANSYS. This was done by securing our 3D printed prototype to a shaker table and vibrating it at a range of 0 to 2000 hertz. Then data was collected by using an accelerometer and placing it on different locations of the prototype during testing. We did 2 of these tests, one with the accelerometer in the middle of the rocket and the other with the accelerometer at the top of the rocket. So this slide has a video where you can see the first node shape occurring during the shaker table test. And here were our results. You can see that the brighter red line was with the sensor placed at the top of the rocket, and the orange line is with the sensor placed in the middle of the rocket. These frequencies occurred at 36 hertz, 285 hertz, and 632 hertz. Again, these were the frequencies of the first 3 bending shapes. So overall, you can see that our theoretical to test values were quite different. And this is due to several differences in the 3D printed prototype and the actual CATIA model, which I'll go into shortly. However, the most meaningful conclusions that we can draw from these values are actually within the ratios of theoretical to test values. And you can see that there's only a difference of less than 1 between all of our ratios, which means that this is reasonably close together, giving us fairly accurate data. So overall, we consider our testing to be a success. Again, because despite the differences in theoretical to test values, our ratio values were all reasonably close together. The differences that we saw are most likely from 3 things. The first being the density of PLA. We didn't know an exact value for this because it's highly dependent on the infill, which is the second thing. And because we left that unspecified, we weren't able to get an exact value to input into our CATIA model. So it was 100% infill with a density that was theoretical. So the difference between the actual model and what we modeled in CATIA is going to be quite significant. And finally, the biggest difference that we likely had was that our rocket was too big to be printed in one whole piece. So it had to be into 3 different sections. So we had several seams with epoxy glue to secure the whole rockets together, which again would not have occurred in the CATIA model, creating structural differences when it came to the ANSYS modeling. However, despite all of these differences, because our ratios were relatively close together, we consider this to be successful testing and accurate data. So that concludes our presentation for the structural dynamics project.